So the next talk is from Pirmin Schlicke.
Yeah, thank you very much. And I was super happy to be in the first session of the speakers, but now after these three amazing talks by Lance, Maxia, and Luciana, it's a really high bar. And well, could also be the beginning of a really funny joke, right? Anyway, so yeah, I'll be presenting some what I think super exciting stuff that we did a couple months already at MD Anderson and Heiko Enderling's team. And yeah, so the whole idea is to use data that are clinically routinely available in the clinics. And one type of these data is usually histopathology that you acquire during diagnosis. And yeah, I'll show you a technique, a method, how you can infer dynamics from those. Now, what dynamics am I talking about? If we look at the cancer hallmarks as published in 2000. I do know there are a couple of newer versions already, and it's 12 or 16 now. I actually don't know, but I guess we can all agree that proliferation and invasion in surrounding tissue are two important key dynamics that form cancer hallmarks. Luckily, we can model these quite easily. So for example, with a partial differential equation looking like this, where you have some function for the proliferation and some dispersion in space, diffusion, shown are a couple different parameter combinations here for the exponential growth. So the simplest approach you can think of, but this has already been used. And well, so in glioma patients where you have some very specific data available, MRI. So what you have here is T1 and T2 images that are taken at two distinct time points. So you have 4 images available to calibrate exactly the equation I've shown you before with, I believe it was with logistic growth. Right? And also was shown that you can identify the relation between the proliferation rate and the dispersion from a single time point. Still, you need these 2 images, but in glioma, that's not a problem because that's standard of care to acquire them. That has been shown, and it is super useful, actually. So if you have the data available to identify the proliferation of these tumors, the proliferation rate that I've just shown you, then what is known is that highly proliferative tumors are more susceptible to radiation. And that is exactly what Kristen and her team have shown a couple of years ago already. So the upper method is taking these 4 images from 2 distinct time points. But also what you can have is identifying the fraction again from one single time point and identify a phenotype of less diffusive tumors. And you will see that they will respond better to chemotherapy. Now that's super awesome, but there are several limitations to this method. First one is, if you want to identify the proliferation rate, you need these 2 time points. Now with glioma patients, it's a bit unclear, do we really have the time to wait to acquire that second time point, right? Because that's usually a cancer type where it's really urgent to make treatment decisions. And secondly, you need MRI. That's standard of care for glioma patients, but not for other cancers. What can we do with other cancers? And I'm going to show you a technique now that is based on H&E stained tissues. So this is from tissue microarray, H&E stained tissue as used in the diagnostics. So that's basically how they identify the tumor in the clinics. And please appreciate the following animation. It took me too long to align these 2 pictures. Thank you. And what you can have here, so what we identified here are the cell locations on the slide. Interestingly, we did not stratify for cell type yet. So just any cell that is on that slide is being segmented by its nucleus, and you get a specific position on the 2-dimensional coordinate system, coordinate space here. Now, there are 2 possible spatial statistics that you can use on point patterns. One is the 2-point correlation function. The other one is the autocorrelation of that one in Fourier space called the power spectrum density. That method was actually written together by Stefano, whom most of you may know. And yeah, you can use exactly those on the point pattern that I have shown you before and fit. So you see the two-point correlation function on the left side, you see the power spectrum density on the right side, and you're able to identify the parameters that are corresponding to these spatial statistics. You see the measures directly below. Now, that's pretty cool, isn't it? And there is some application to that one. For example, we have esophageal cancer here. We have a specific population shown on the right side. You have 49 patients, and we have the endpoint of overall survival available for these patients. So we had the diagnostic tissues, the tissues taken for diagnosis for these patients, identified the two parameters, and started stratifying. And this is what you see when you stratify at the median for the diffusion. You clearly see a difference in overall survival for these patients. But we also have the radiation response available for these patients. Unfortunately, not as time to event, but as a correlation. And again, you see on the left side here that the proliferation rate does actually correlate with radiation response. The higher proliferation rate identifies patients that are more likely to respond to radiation. So a bit more detail is shown on the right side, and you can see that the response column is shown again for the high gammas. We have another data set where we used the tissue from the microarray that I've shown you before. There, we were able to identify the cell subtypes. So here we are just looking at the tumor cells from those slides. And we have available the time to event this time for radiation response in terms of local regional control. Again, cervical cancer. This is what you get stratifying for the proliferation rate. Pretty amazing, right? And the cool thing now is that knowing these two parameters for individual tumors allows us to simulate the whole thing, right? So say I simulate with the average values within the two curves. So we have a tumor with higher proliferation on the top with a lower proliferation in the second row. And now we start simulating. The same time cutoff, you can't really spot the difference. Maybe people sitting in the first row can. I can't from here, but that's fine. Now we apply radiation to those. How that looks like is roughly like this. You have a density cutoff, set a safety margin as they do in the clinics, delete everything that is in there, and then you start simulating again forward in time what will happen. And you see these phenotypes afterwards. Does make sense, right? So there is really an explanation to these dynamics, and we are able to identify phenotypes just from the diagnostic histopathology slides. And there is another slide I want to show you because these were just two very specific cancers. We have a couple more. I just cherry-picked some of them, especially the left one, p-value 0.0504. So you can imagine my mood after that, but you can play around a little and optimize, right? So the curve split. That's pretty cool. Yeah, by the way, melanoma on the left, head and neck in the middle, and clear cell renal carcinoma on the right. Well, I think I have to make up some time, so I'm happy to take your questions. These are all the people involved in the work. If you want to get in touch, there's my email address at the bottom, and especially I want to thank funders on the right side. Thank you.
Thank you. Very nice. Questions? Anyone?
Thank you. That's pretty impressive. I was curious, the better response to radiation that you see in the highly proliferative disease or cancers, is that solely because they're proliferating faster, or is it also because they're in invasive cancer, then those invasive cells are probably not going to be in the irradiated region? So I was wondering if you looked into these two different explanations.
Yes. So the question was, oh, you did hear that, right? Okay, sorry. Yeah, so actually it's a combination of both. And the answer is not that straightforward. You do see a correlation when it comes to proliferation, but within those curves, there are a lot of different things going on. So you see different phenotypes within the curves as well. I'm currently putting that together. The manuscript is in preparation. Happy to share more about that later if you want, and I can share you some sub-stratified survival curves if you're interested. But yes, there are certainly some phenotypes within those survival curves as well.
Other questions?
Thank you. Great talk. So if I'm understanding correctly, you're calibrating your model to the histological data to pull out these parameters. I was wondering what the actual structure of your model is.
Yeah, in that case, the structure. Oh, I didn't put the copy in. So basically, it's exponential growth here. Exponential growth and dispersion. That's a whole model.
Thanks.
And again, the histology is based on all cells, not just the tumor cells in general.
Thank you for a really cool talk. I have a quick question. You at the one point you mentioned you were focusing on the tumor cells in these slides. Have you looked at other cell types like immune cells?
We try to. Unfortunately, I did not finish this yet. There are some ideas to also look at the interaction of tumor cells and lymphocytes. And there is certainly data available that we will check, but I can't, unfortunately, at this time, I can't tell you more about that. But great question. Thank you.
But is that also correlated to patient outcome? Because it's been shown that proliferation is not related to patient outcome. We can simply kill those cells by chemotherapy. And also hypoxia. This is all you show is like in normoxic zone that are proliferative cells located in. We know that tumors are not just simply normoxic, oxygenated tissue.
So to break down your question, that was if the proliferation also correlates with survival, right? That was the first question.
Because you showed proliferation correlated to radiation response. Is it also correlated to patient outcome? Do these patients survive better? No.
In this case, not.
In any case, we know that.
Yeah.
Okay, I think we'll close the session here. We have a break now. We'll come back at 3:05, 5 minutes later than scheduled.